Now that we've introduced this idea of enthalpy, which essentially describes the movement of heat energy in and out of a system, we can start looking at how we calculate enthalpy for different reactions and some other relationships that we can derive from these quantities. So now we're going to introduce thermochemical equations. A thermochemical equation is a balanced equation that includes the enthalpy change of that reaction, which we indicate as delta H of the reaction. Now, there's two important aspects that we have to keep in mind with regard to our enthalpy changes. So the sign of our delta H is going to indicate whether the reaction is exothermic or endothermic. Okay, so we saw this previously when we were talking about these different processes, right? If I have energy leaving my system in the form of heat, then that's going to be an exothermic process, and the sign on my delta H is going to be negative because overall the energy of my system is decreasing. It's losing some energy in the form of heat. We saw the opposite case for an endothermic process, where if we have heat entering our system, then we're going to have an increase in the enthalpy of that system, and our delta H will be positive. And this next bullet here says that a forward reaction has the opposite sign of the reverse reaction. Okay, so let's think about this. If we have some generic reaction, okay, we'll just say A plus B yields C. Now, let's say that the delta H is negative for that reaction. Now, what this bullet point is saying here is that if we have the reverse reaction, okay, so if we now have C decomposing into these reactants, A and B, then the delta H is going to be the opposite sign, okay? So now if we take the reverse reaction here, we're saying that heat is moving into this system, okay? So whenever you flip one of these thermochemical equations to represent the reverse reaction, you always change the sign. Okay, so a forward reaction has the opposite sign of the reverse reaction. Okay, so the sign is our first important consideration, and we need to recognize that the magnitude of this change in enthalpy is proportional to the amount of substance that we have. So we're going to see examples of thermochemical equations, and when they tell us the delta H of that process, it directly corresponds to the amounts of each substance that are involved in that process. Okay, so if we have more or less substances than what's represented by my balanced equation, then I have to account for that by adjusting my delta H. Okay, so we're going to see examples of these balanced thermochemical equations and how when we're given a delta H value for a certain process, we recognize that it directly corresponds to the amounts of substances that are present in that particular reaction. Then, as you might be able to infer, we're going to be able to use the value of delta H the same way that we use molar ratios, okay? In chapters 3 and chapters 4, when we introduced this idea of using molar ratios, because we said that the substances in a balanced equation are stoichiometrically equivalent, we're going to see the same sort of idea here. So we're going to have stoichiometry of these thermochemical equations. Okay, because if we know some amount of heat that was absorbed or released during some process, well, the delta H that's provided is going to correspond with the coefficients in our balanced equation. Okay, so then we can start to do some stoichiometry using this delta H as a conversion factor. So if I know how much heat was transferred during a process, then I'm going to be able to make inferences about substances that are involved in that process. We'll go through a couple of examples together. Now, before we get on with the application of this, there's a couple things that we want to keep in mind when we're doing stoichiometry of these thermochemical equations. Something that we're going to notice is that we're using these fractional coefficients to balance equations. Okay, so oftentimes you're going to see something like 1/2 of molecular oxygen or 3/2 of molecular nitrogen. Okay, and this is kind of funky, right? Because in our first unit, we always said that we needed to have whole number coefficients. The reason we start to see these fractional coefficients is because now we're going to be talking about things like the standard enthalpy of the formation of some compound. Okay, and typically we will represent the magnitude of that change in enthalpy with regard to 1 mole of some substance, okay? So we take a look at something like this, okay? We see the formation of sulfur dioxide, and this equation is just trying to represent the formation of 1 mole of sulfur dioxide. We have this 1/8 of elemental sulfur, which is S8, okay, because I'm just trying to say 1 sulfur atom. But I can't write something like this, because the elemental state of sulfur, okay, the substance that's reacting here is S8. So if I only want 1 sulfur atom, because I'm just looking at the formation of 1 mole of this substance, then I'm going to put this funky coefficient here. Okay, we do all of our calculations the same way. It shouldn't scare you too much, but you should be aware that we're going to see stuff like this. Okay, and it's because typically we're specifying this delta H for the formation or the decomposition of 1 mole of some substance. Okay, so we could write this like S8 plus 4 oxygen gas yields 8 moles of sulfur dioxide gas. So this is more like what we saw in our first unit. But if we change the amount of substances here, okay, so if now I'm talking about the formation of 8 moles of sulfur dioxide, well, what I'm going to find is that I would have to multiply this change in enthalpy by 8, because this value that they're providing here is the change in enthalpy associated with the formation of 1 mole of sulfur dioxide. Okay, so more conventionally, we're going to see something like this. And this provides a good segue into our next important consideration when we're doing these stoichiometry problems. So for a particular reaction, a certain amount of substance is thermochemically equivalent to a certain quantity of energy. Okay, so keeping in mind this same example here, let's take a look at what we're saying. We're saying that this 298 kilojoules is thermochemically equivalent to each of these quantities of substance. So it's thermochemically equivalent to 1/8 of a mole of sulfur, 1 mole of oxygen gas, and 1 mole of sulfur dioxide. Okay, so keeping in mind the concepts of mass conservation and energy conservation, if we change any of these amounts of substance, then it's going to change the value of our delta H. Okay, it's going to change the amount of heat that is released by this process. So this thermochemical equivalence is saying that we have a certain amount of energy associated with fixed amounts of any substance in any process. Okay, if we change any of these coefficients here, well, we should know that we would have to change all of them, right? If I want to react twice as much oxygen, then I'm going to have to react twice as much sulfur, and I will get twice as much of my product. Okay, and following suit then, we would have twice this change in enthalpy, twice as much heat being released. So we're going to use this fact, we're going to use this sort of underlying concept here to do these stoichiometric calculations. We're going to be told that some amount of heat is being transferred during some process. And we're going to have a balanced equation like this with some respective change in enthalpy. And if we know how much energy is being transferred, we can use this as a sort of conversion factor here, okay, to say, well, if that much energy was absorbed or released, then this much of substance A should have reacted or been produced. So as is the case with most of the concepts that we've learned, practice is going to be key to really understanding this. So let's take a look at a couple practice problems here. We're going to use the enthalpy change of a reaction to find amounts of a substance. The problem states that the thermal decomposition of aluminum is represented by this equation here, okay? I have aluminum oxide, I'm applying some heat to this substance, and it's decomposing into its elemental components, okay? And it tells me that this reaction requires 1,676 kilojoules of heat, okay? So we have a positive value on our enthalpy, which means we have heat entering the system, right? And we see that here. This is a thermal decomposition. So we're heating up this reactant here, this aluminum oxide, and we're trying to figure out if 1,000 kilojoules of heat were transferred, then how many grams of aluminum can form? Okay, so we have these coefficients on each of our substances, right? We can say that there's a 1 in front of this aluminum oxide, and for every 1 mole of aluminum oxide that decomposes, we have 2 moles of aluminum formed and 1.5 moles of oxygen gas formed. So where would we start with something like this? Well, we always want to start with the information that they've given us, right? So they said 1,000 kilojoules of heat were transferred. So 1,000 kilojoules of heat were transferred. So if I have 1,676 kilojoules of heat transferred, these are going to be my respective amounts of each of these substances, okay? But it's saying I only have 1,000 kilojoules transferred. So here is how we're going to use this enthalpy as a conversion factor. We're going to say, well, from our balanced equation, we see that for every 1,676 kilojoules of heat that are applied, we have 2 moles of aluminum released from this compound, okay? So 2 moles of aluminum, okay? So here's our thermochemical equivalence. For every 1,676 kilojoules of heat that enters this system here with these respective amounts of each substance, I can decompose 1 mole of aluminum oxide into 2 moles of aluminum and 1.5 moles of oxygen gas. Okay, so this is how we derive this conversion factor here. We use our balanced equation and the delta H value that's provided to us. So if we were to stop here, we would see our kilojoules cancel out, and we would figure out how many moles of aluminum were formed. But it's asking us how many grams of aluminum can form. So we're going to have one more conversion factor here, using our molar mass of aluminum. Okay, so we would say, well, in 1 mole of aluminum, I've got 26.98 grams. So let's run this back one more time. Okay, they told us 1,000 kilojoules were transferred, and we know that for every 1,676 kilojoules of heat that are transferred, 2 moles of aluminum are allowed to form. Okay, so we went from kilojoules of heat to moles of aluminum, and now we're going from moles of aluminum to grams of aluminum using the molar mass of this substance. So we would take everything in the numerator multiplied together, divided by 1,676, and we should find something like 32.2 grams of aluminum. Okay, so if this amount, if 1,000 kilojoules of heat were transferred, then 32.2 grams of aluminum must have been produced. Okay, we applied this amount of heat, we had this amount of heat absorbed by our system. Okay, 1,000 kilojoules of heat entered this chemical system here. This initiated the decomposition of this aluminum oxide, and it yields these elemental products here. Okay, based on the coefficients that we have in this balanced equation, we were able to assume some thermochemical equivalence and use this conversion factor here. For every 2 moles of aluminum, I have 1,676 kilojoules of heat. Once we had the moles of aluminum produced, we determined how many grams that was. Let's give this next problem a try. This one is the decomposition of liquid hydrogen peroxide, and it's represented by this equation here. We see the associated delta H is negative 196.1 kilojoules. So this is an exothermic process, and as long as we have 2 moles of hydrogen peroxide decomposing, then we'll have 2 moles of water formed and 1 mole of oxygen gas, and this value here represents the amount of heat energy that is released for these respective amounts of each substance. Okay? So now the question is asking how much heat is released when 652 kilograms of hydrogen peroxide decompose. So, like always, we want to start with what they gave us. Okay, they said we have 652 kilograms of hydrogen peroxide. So 652 kilograms of hydrogen peroxide. And I want to know how much heat is released from this amount. Okay, so I should end up with some answer in kilojoules, right? Because I'm told I have this mass of hydrogen peroxide decomposing, and I want to know how much energy that's going to be releasing in the form of heat. So eventually I'm going to want to use something like kilojoules per mole, right? Because we said we have this thermochemical equivalence with all of our substances here. So if I have 2 moles of hydrogen peroxide decomposing, I have 196.1 kilojoules of heat being released. So I'm going to want this mass to be expressed in moles. So if I have 652 kilograms of hydrogen peroxide, well, first I need to convert this to grams so that I can eventually use the molar mass of this compound to figure out how many moles I have. Okay, so let's start by converting this mass into grams. I want my kilograms to cancel out, and I know that in 1 kilogram I have 1,000 grams. Now that I have this mass expressed in grams, I can figure out how many moles of hydrogen peroxide I have using the molar mass of this compound. So, in 1 mole of hydrogen peroxide, how many grams of this substance do I have? And the molar mass of hydrogen peroxide turns out to be 34.016 grams. And if I were to stop here, it would tell me how many moles of hydrogen peroxide I have decomposing. But I want to know, if I decompose this amount of this substance, how much heat is going to be released. So this is where I use my enthalpy value and set up some sort of enthalpy ratio based on the coefficients in my balanced equation. Okay? So I said that all of these amounts of substances are thermochemically equivalent to this change in enthalpy here. So if I want my moles to cancel out and I want to be left with units of kilojoules, then I'm going to take a look here and see that, well, for every 2 moles of hydrogen peroxide that are decomposing, I have this amount of heat that's released. Okay, so I have 196.1 kilojoules that are released if I have 2 moles of hydrogen peroxide being decomposed. In this case, I have a lot more than 2 moles being decomposed, okay? And I'm solving for this here. They told me I have 652 kilograms. I'm converting that mass into moles, and then I'm using this sort of enthalpy ratio from my balanced equation. So I went from kilograms to grams using the respective conversion factor. I went from grams of hydrogen peroxide to moles of hydrogen peroxide using the molar mass of that compound. And then I went from moles of hydrogen peroxide to some amount of heat energy using this thermochemically equivalent quantity based on my balanced equation. So it ends up being a pretty large quantity of heat, something like 1.88 times 10 to the 6 kilojoules of heat. Okay, so that's saying if I have 652 kilograms of liquid hydrogen peroxide that's being decomposed, then 1.88 times 10 to the 6 kilojoules of heat are going to be released by that process. This amount of energy is being released from my system to its surroundings in the form of heat. Now, just for good measure, I put one more example here, okay, so we can get a little extra practice with our thermochemical stoichiometry. Now, I didn't feel like making a new slide, I just pulled this out of the textbook, so bear with me on the presentation of this, okay, but we have our balanced equation and its associated change in enthalpy, and we want to know how many kilojoules of heat will be released if 25 grams of elemental sulfur reacts, okay? And here we have an example where we have one of these funky fractional coefficients, right? But we're just going to treat this like any other coefficient. So we're going to start with the information that was provided. We have 25 grams of elemental sulfur reacting, okay? So I'm going to write 25 grams of elemental sulfur, okay, S8. This is our most abundant form of sulfur. This is how it occurs naturally, which is a molecule of 8 sulfur atoms, okay? So we're going to see, if we take the molar mass of elemental sulfur of S8, we need to take the atomic mass units provided on the periodic table and multiply that by 8, because the atomic mass units, or what we know as the molar mass that's provided on the periodic table, is for 1 atom of sulfur, or 1 mole of sulfur. But sulfur in its elemental form actually occurs as a molecule of 8 sulfur atoms, okay? So keeping that in mind is going to help us with this next step here, because eventually we're going to want to use some thermochemically equivalent quantity to figure out how many kilojoules are released from this reaction if I have this mass of one of my reactants, right? But if I want to use that thermochemically equivalent quantity, okay, we can call it something like an enthalpy ratio. If I want to use that enthalpy ratio, I need to have my amount of any particular substance expressed in moles, okay? So I want to figure out how many moles of sulfur this is. So I'm going to say that in 1 mole of elemental sulfur, I've got 256.56 grams. Again, that came from the atomic mass of sulfur times 8. So this conversion here will tell me how many moles of elemental sulfur I have. And now I can use this ratio from my balanced equation. Okay, I'm trying to figure out how many kilojoules of heat are going to be released if this amount of sulfur reacts. Okay, and based on this balanced equation here, I see that in this process, for every 1/8 of a mole of elemental sulfur, I have negative 20.2 kilojoules released. So I was given some mass of elemental sulfur, and I converted that to moles using the molar mass of this substance. And now I'm going from moles of sulfur to amount of heat released, using the fact that for every 1/8 of a mole of sulfur that reacts, 20.2 kilojoules of heat are released. Okay, we always have to have this thermochemical equivalence, because this tells me the change in enthalpy for these respective amounts of each substance, right? If I have different amounts of any of these substances, then my change in enthalpy needs to be adjusted accordingly. Okay, so that's exactly what we're doing here with this conversion process. Okay, so now we would take 25 times negative 20.2 and divide it by the product in my denominator. And I should get something like negative 15.7 kilojoules. So this is the amount of heat that is released if I have 25 grams of elemental sulfur reacting to form hydrogen sulfide. So there should be lots of practice problems in the book and online. I don't think that you'll get much practice with this in ALEX. I can't remember if they specifically had a topic for our stoichiometry, but tons and tons of practice problems online, okay? Just look up stoichiometry of thermochemical equations and you should get similar practice problems to these, okay? Make sure you understand this idea of thermochemical equivalence. At the core of this application here is our law of the conservation of energy. I can have some change in enthalpy associated with a given balanced equation, but if I increase the amounts of any given substance in that process, then I'm going to increase the amount of energy that's absorbed or released during that process. Okay, so we can derive something like this based on some of these foundational ideas.